over to you, Pete.
Right, and now you can hear me. Is that all good? Great stuff. So yes, I'm Pete Bailey. I work for Instron in the UK. So I'm just wondering what to do with the image here. Let's do that, then I can see what's going on. It's been a really nice couple of days, really interesting presentations. And as I find myself being one of the more senior people these days, rather to my distress, I guess it's my job to say I'm very impressed with everyone. You all do really well. But in all seriousness, great presentations, everyone. So I've got if you'll pardon the slightly terrible "Dad's trying to be cool" title here of #NoFilter. Well, I'm at that point in my life. I have a 12-year-old and a 14-year-old, so it's my job to make the small children, make the children try and moan and say, "Oh, Dad, that's terrible." So my point here was, obviously earlier in the year there were lots of people staying at home and posting lovely photographs in the great weather, saying "no filter." And what this made me think about was, especially over the last couple of years, I see various things where people do things to their data. They filter it or they smooth it, and it's not necessarily as good an idea as they originally thought. So I thought that would be an interesting thing to talk about fairly briefly, without getting into anything too specialized of one thing or another. There we go. So Instron, in the unlikely event that anyone doesn't know, we make mechanical testing equipment. That's tension or compression or torsional loading. Also impact by drop weight or swing hammer, melt flow rheology, and we have a sister company, Instron Structural Testing, who do really big rigs, 16, 40 actuators even, full structural testing on automotive usually. Personally, I work for Dynamic Systems, and we're based at High Wycombe near London. We make fatigue testing and fast-moving things, broadly speaking, and we do the transducers, the data acquisition, the control electronics, and the software as well. Certainly the test control and recording software. You can see broadly the sort of family of machines that we make in the UK. They do low-speed testing machines are made in the United States, and the melt flow and impact are over in Turin in Italy. We do make slightly bigger machines than some of those, than the ones you can see on screen here, but the biggest ones are about 5 times as tall, so don't really fit in quite the same shot. So yeah, that's the sort of thing that we do as Instron. My own work is supporting all of the stuff that people like yourselves do using machines, and whether it's helping you to create a new system or buy one that's going to do new stuff, or use the one you've got. So as our last presenter said, hopefully Instron will have something interesting to show us. Well, we have the compulsory things breaking. When someone who doesn't know anything about the business asks me what I do, I say work for Instron. We break things accurately. So my little movies here, which hopefully they're coming through with reasonably for some of you. These are all high-speed tests at between about 2 meters per second up to about 15 meters per second, which is just one fairly specialized part of what we do with the hydraulic machines. So what I was going to talk about today, what people do with raw data. So when you're recording experimental data, it's always messy in some way. I say usually, if you look closely enough, it's always messy. There's always noise in some way or some level of uncertainty. And as researchers, we always want to find order among what might look like chaos. occasionally we fail, and there's just no way to have the ducks in the row. There are only squirrels at a rave. So we find ways to tidy things up if things are a little bit untidy. And this is very much certainly within the physics, applied physics community. We tidy things up, we clean up our data, and we're in search of truth and beauty, at least in our terms of thinking about it. So the first thing that people ask me about when they're talking about measurements is accuracy, which is excellent, well and good, but you should also be thinking about precision. So how much noise is there? How reproducible and repeatable is that measurement? Now I'm going to pick up those two second terms a little bit more specifically, because people don't always differentiate well. Repeatability is about, if you do the same experiment 5 times, do you get at least broadly comparable results? If you don't, then there are a whole range of questions about, is your hypothesis sensible? Is your experimental design sensible? Reproducibility, on the other hand, is about, you've done your study, you've written it up, you've published it. Can someone else in another laboratory in Canada, Japan, Germany, pick up on what you've written and basically go through it, make their own version, and reproduce the same, or at least a very similar result? So really what we're after as researchers is facts. Facts, not opinions. This is over the door at the Testing Works in London. David Kirkcaldy got fed up with no one being able to give him decent evaluation of steel products. So he set out to set up his own companies to do so, and created the first, something roughly equivalent to a 1 meganewton load frame, completely water powered. The other image I've got here, if this is quite an old film now, Indiana Jones, and he's talking about, he says, archaeology is the search for fact. If you're looking for truth, the philosophy class is just down the hall. And this idea of what's the true value it's quite an interesting concept, especially once you get down to trying to extract meaningful information from quite noisy data. So I mentioned filtering, going back to my title. Now I should be very clear. Filtering has very specific meaning, certainly in terms of signal processing. Now this is typically its digital function in modern times, but equally it could be an electrical device or even a mechanical system. And what it does is that sort of filter, it smooths out your data by attenuating particular frequencies. Now you say, what's frequency mean to me? I'm doing a static test. Now the background of this is all sorts of audio and radio technology, but when we look at it in our context of mechanical testing, it's also about rate of change in a signal. So the noise on a slowly ramping load signal is actually, the noise in the background there is far higher rate of change. And that is what you want to reject, or at least the right parts of it. So, and this isn't, I'll put my hand up, this is absolutely not my area of work. It's a very complicated thing. Lots of information out there, lots of great people working in it. Go look it up. But it's a particular thing, and it happens usually without a lot of our community knowing that it's going on under the hood inside the data acquisition system. There are times when you need to be aware of what it's doing. You can almost always change the settings, and do be aware of that, especially if someone else has set up the test for you. Maybe they've done something strange, so always check. Something that I think everyone in this meeting will have some direct personal experience of is smoothing, averaging, and fitting of your raw data. Your raw data as you've taken away from a text. And we do sort of smoothing operations, averaging operations to clean up, and it's something that anyone can do very easily with spreadsheet or MATLAB or your data processing method of choice. You might average endpoints 3, 7, whatever, or you might do a linear fit to a similar number. Equally, when we come to trying to extract information from a data set, very common use is linear regression or fitting a tangent, or maybe a power law in some cases. And you're trying to find something interesting, some way of describing and finding a clean and simple method to describe something. Great. Modern times, really easy to do this, easy to set it up. It's equally easy for people to set it up and not actually think about what it's doing and not necessarily get a good answer. A little comic here, which I have lifted. This was actually in portrait format, but I've sliced it and put it side by side. Credit to XKCD comic as written by Randall Munroe. If you've not come across it, absolutely go and look it up. I always find it very, very amusing. And the point he's making here is you've got a splat of data points. You can do sensible things with it. You can do things without any knowledge and come up with possibly utter nonsense, especially if you look down towards the lower left of the screen here. There's also an aspect, and I think the experimental mechanics community are pretty good about this, about understanding what should be happening first and then trying to make a sensible model. So the point I want to get across is make sure you know what you've done within your test. Make sure you know what data you've collected. And in my abstract, I promised 3 cautionary tales, examples of what can go wrong. And first one is finding peaks, or possibly not peaks. And second one, ill-advised filter settings and distorting the curve. And third one is assuming the way you analyze this is obvious and there's only one possible way to do it, then discovering that's not entirely true. Now, the first 2 of these, I've not got true real-life examples to show you. Most of those end up being a little bit customer sensitive, but you can do a demonstration for yourself, as I've done to illustrate my point here. You can do this and you can set it up and prove to yourself the way these things behave, just using Microsoft Excel. It's not fantastically difficult to look at the effect of smoothing and how you smear out data, especially if you have a sharp feature. So, first example, find the peak. No, not that peak value, this one. Now, honestly, I've seen over the last few years, there are 1, 2, 3 inquiries come in, either to my colleagues, and occasionally they go as far as my desk, where people are saying, well, in my data, it's recorded this, and when I was watching it on screen, it went actually a bit higher. So why is that? And it really does come down to overfiltering. The particular place you see this is in something like a low cycle fatigue test. Now here you'd usually use a triangular or a trapezoid wave, and you'd have a sharp turning point. And the sort of setups where you do this often mean there's relatively high noise. So in consequence of that, you then apply a fairly low pass filter. So that's smoothing out the data quite aggressively. And it means you get nice data for interpretation, and it means you get much steadier control of the machine. But look at my graph on the right-hand side here. So I've decided that my true line, that black is my true signal here, and it's going up to exactly 50 at the point of the triangle there. So then I've kind of made, well, let's do a simulated signal with a little bit of noise there. Orangey yellow line with black circled dots. And you can see that now here, that's actually by chance, we've got a positive piece of noise, and it's boosted up the actual peak. By blind luck, we've sampled exactly at the peak to over 50. Now another, I'm not going to dive into this much, but if you don't sample often enough, then let's look at the red circles where you've taken a lower sampling interval. You've actually missed the peak, and suddenly you're now way down. The nearest point to the peak, and therefore the highest point in your data set, will only be 48. We've lost a considerable proportion of our peak value here. So do make sure you have enough of a high enough sampling rate if you possibly can. Obviously, there are cases like Harry was saying earlier, the frame rate on your camera can be really important if you're doing some sort of imaging studies. Third, last point here, this is illustrating what I mean about smoothing and a filter. So this green line is simulating a filtered signal, and that's cutting out, that's doing a really great job. You look at the slope up, it's doing a great job of cutting out the noise and giving you a much closer approximation to the true signal, at least most of the way up and most of the way down. You'll see it's offset, and that's because when you apply a filter, it can only see what's in the past. Therefore, it introduces a time lag on the signal. What's unpleasant about it is you can see it's taken the top off of our triangle. And in fact, it's given us not as bad as the undersampled data, but it's taken the peak down. And this filtering and this data logging rate, that's the answer which I have to these inquiries which come in. Very briefly, this is a much more unusual one. But if you have something that's not actually linear, and you filter and you do a monotonic test, what the filtering does, as I just showed you, is it smears things out, and therefore at the beginning of the test, it can do horrible things, distorting your curve. So this is my little sort of very crude simulation where the true signal is the blue line at the top. And then you do a little bit of smoothing to that, a little bit of equivalent to filtering. And suddenly you see, rather than a curve all the way up, you've actually got an almost linear section at the bottom. And then you smooth, then you put the filter way down, apply far too much smoothing, and you can see now the green line is actually a very, very different shape. And the most obvious warning is that at the far end where it breaks, that's not, you would see this in the lab as a sharp break, and you look at the data and it's going down in a constant slope. Now that is clearly not right and would give you a very obvious warning. But genuinely, there are people who, this is something that I think has caused problems, and I've had a couple of quite difficult conversations where people have been presented data where there's a nice linear region, and then you look back to the raw data and you try and repeat the experiment or reproduce the experiment, and actually with the true raw data on the same batch of specimens, it's a different curve. So watch out. Last one, very briefly. This is a real example. So fracture toughness. K1C is brittle fracture toughness. For anyone who's not familiar with this, you have a crack in the specimen. You load it up until you get a critical failure, and there are very well standardized ways of doing this for metals. ASTM 399 is probably the most popular one we see globally, and it's pretty straightforward. You find the linear region. This is a metal specimen, so there is always going to be a linear region somewhere down the bottom of the loading. You find that, you find the slope, and you do an offset from the slope. But fitting the slope affects where you find the critical point. Well, I mean, fairly obviously, since you're doing an offset from there. But it actually affects it more than you might think. So ASTM E399 is this standard which I mentioned. It's been out there for a long, long time. And people thought it was, absolutely straightforward until Mark James and Pete McKeegan, who I'm lucky enough to call friends, did a study, and they handed the same a group of data sets, real data sets, to 15 labs and said, off you go, lads. Give me answers on this. And they discovered that in many cases it was fine. But actually, this graph on the right-hand side here, you can see that certain specimens, maybe some of them were noisy data, some of them were odd-shaped curves. The way that people read the specimen led to huge variation in finding that critical point. Up to 20% variation in determining the critical point. That's a 20% variation in the result you get from the same data set, which is certainly a cause for concern. Now, since that time, there's been a lot of work done, and the standard now is much more specific about how you find the linear region, what is the linear region, and in fact, we're in the process of running another round robin over the next few months to try and prove that we've improved matters. So, last slide about the ideas I'm talking about. Statistical significance is an idea that you'll a phrase that you'll hear. Now, honestly, I'm not keen on statistics. It was almost my least favorite modules in A-level and an undergrad degree. I'm terrible at applying the equations myself. However, they are important. And it's really important to understand the point. Because if you don't, then you end up doing something like this. You end up with a tiny sample sizes, and you can end up with a huge scatter, and actually just the bias within that scatter gives you a different average. But with a small sample size, it's really, really not convincing. So I have genuinely seen very occasionally people present a graph that's a bit like this and said, well, obviously option one is considerably better than the others. Well, it looks like it, but your data is not actually enough to convince me. Go and get more data and come back. Now, descriptions such as statistically significant, they're not always relevant when you're doing early stage research, when you're doing proof of principle. That's absolutely fine. But I think we all need to remember that the object of the exercise is that we're engineers, we're applied scientists. We're trying to deliver something that's going to help a real world solution. And that is the point when this stuff really is essential. So, wrapping up, we're all interested in the measurements above all else in experimental mechanics. Measurements and models and how they fit together. What I always say to people is think about the whole system. Yes, there's your thing that you're interested in, but you do need to think about the whole experiment. And do be specific when you report about it. It's quite important. So I have this question which I say to people, you should ask yourself, what can go wrong with my experiment before you start? Now, I know that sounds pessimistic, but actually the point of this is think about all the ways it can go wrong, and then you can try and mitigate anything that's a high risk and try and make sure you've done everything you can to avoid it. But also when you're actually doing the experiment, you can watch out for other problems and hopefully spot them soon before you've spent hours collecting a whole batch of rubbish data. So, general ideas, maybe not the most exciting thing in the world, but it really makes a difference to the quality of your work, how convincing it is to other people, and how useful it is commercially, and that sort of thing. So, that's all for today. Thank you very much for listening, and I hope that wasn't too tedious.
Thanks, Pete. So, are there any questions from the audience? I know, particularly even yesterday, there was a lot of questions in the area of statistical analysis. So yeah, the floor is open. I guess I had one question for you, Pete. With respect to all of these considerations, there's been a wide range of tests that you've seen over the last couple of days. Have there been any sort of standout examples from your experience where these sorts of considerations go very wrong? Say with standard sort of fracture tests, tensile tests, these sorts of things in terms of the quality. Is there any advice or consideration?
No, I think with what I've seen, and I'm sorry I couldn't join you the latter part of yesterday afternoon, but what I've seen this morning and yesterday morning, it's really nice. And actually, I don't find it surprising in this particular community that that people are paying attention and watching out for stuff. Who was it? Was it Mr. Sheen, I think, was presenting about or was it Inal who was presenting about the interlaminar toughness, the adhesion, and I thought that's an interesting illustration. No criticism there at all, but that's the sort of thing where you get this huge variability. And having worked on composite stuff myself in the past, I know that it's what you expect. And within that community, you might glance at that and say, that's not too bad on that variability. But don't forget to step back and if you're presenting to a different audience, and just remember that they might not have your perspective on it. But no, I think everyone's been really careful and sensible, and it's interesting talking about some of the talks about where we're talking about interpolation within models. Is actually I've been talking with some people about that recently on real data. No one's actually in this group. No one's been really presenting about fatigue work, but I've seen a number of fairly early stage presentations, and they've put up a fatigue life curve, and they've only got like 5 or 7 points on it, and it's like, oh no, don't do that. That's or at least say something about it. This is really early stage. So yes.
So yeah, I guess getting that context of your field and getting a feeling for these types of tests.
I think I started down that path quite early, because when I did my PhD, I was doing something where it was an overlap of 3 different areas, and so basically anyone I had to present to, I had to present the broad ideas of all 3 before I could talk about my work, because no one was going to understand, or no one I was meeting was going to understand all of it. So yeah, always think to take a step back. It's really useful.
Yeah, and that's where these sorts of events, but also when you go back to your groups and everything. I've been, especially in this sort of time when you're not in that office environment necessarily, you perhaps don't always have those coincidental coffee break type discussions with your colleagues, but this constant review and discussion just helps refresh and highlight potentially these aspects of, say, repeatability and things like that. This is definitely something which I've found that I've had to emphasize a lot more with this sort of remote and intermittent type of work, because it can be easy to lose sight of the bigger picture with all of it. So yeah, no, that's a good point. I think at the moment we are awaiting the final scores. So what I was going to suggest is, since we didn't have a full house for a group picture, we could perhaps take one one more today, and hopefully would have caught everyone before we go to the closing ceremony. But thanks, Pete, for that talk.
No problem.